Hi, I'm Lisandro Maders, the Head of Sales and Marketing at ENGYS and the General Manager of ENGYS Brazil. And today I will show you what's new in the just released version 4.2.0 of Elements, ENGYS open source CFD software for automotive design applications. In case you still don't know ENGYS and Elements, let me quickly present it to you, but if you do, feel free to skip this part. ENGYS is a private company that develops CFD software using open source technology and also offers a range of services including consultancy, custom CFD code development, HPC on demand, and training. Elements is one of the open source CFD software solutions we offer, and it's used by the major OEMs in the automotive industry. One of the reasons of Elements' success is the external Aero Wizard. The external Aero Wizard has been developed to guide the user through the various steps required to complete an external aerodynamic CFD simulation in a virtual wind tunnel using a set of predefined modeling best practices. The default best practices provided with Elements have been validated against more than 200 wind tunnels tests to deliver highly accurate drag predictions for a variety of vehicle shapes in open road operation. You can also create your own best practices by editing the existing configuration files with the help of our detailed documentation or with the help of our technical support team. Another reason for Elements' success is its open source nature. It means that all Elements customers can fully access its source code. But also another great value associated to the fact that Elements is open source is its unlimited scalability. Unlimited scalability means that you, as a CFD user, can run as many simultaneous simulations in as many computer cores as you have available, without the need to acquire extra HPC licenses. And basically, that's what ENGYS is here for, to help you unlocking the full potential of your CFD enterprise applications by the use of open source technology. Elements version 4.2.0 includes several new features and improvements, and most of them were focused in this version on improving automation and user experience. Starting with the new features of the external Aero Wizard, we have a new default template called Open Road Elements High Fidelity. This template provides improved near-wall layer resolution and finer volumetric and surface mesh refinement settings. Another enhancement is regarding Elements assembly types. In previous versions, the set of vehicle geometry files of assembly types was limited, in terms of boundary conditions, only to the boundary conditions available to walls. In this version, we have generalized the boundary type for assembly types, meaning you can now define, for example, a suction inlet or an outlet blowing, air intake, which wasn't possible until this version. Another default template that was added is the Open Road Elements FEAF, enabling you to model thermal flows and also support for defining multiple rotating components directly in the configuration files for modeling, for example, rotating fans. In previous versions, adjusting ride heights required moving the car's body, which limited precise aerodynamic comparisons. Our latest version introduces a rotated wind tunnel approach. The car remains fixed while the wheels adjust, and the wind tunnel rotates to align to it. In terms of reporting, a new monitoring function called ventilation drag was added. In the same way that regular longitudinal drag is the resistance force experienced by a body translating through a fluid, ventilation drag is the resistance moment experienced by a body rotating in a fluid, for example, a wheel rotating in air. Even though the main aerodynamic resistance experienced by an automotive vehicle is from longitudinal drag, it is known that ventilation drag can account for up to 25% of the total drag resistance. Finally, the Elements Report tool presents several enhancements such as higher resolution plots, increased quality graphs, improved layout for tables, user-defined options for editing the default report template, and improved case comparison for side-by-side design lookup. The first feature I will talk about is our Python journaling system. In previous versions, we released a feature which enabled users to record any action performed in the graphical user interface into Python scripts that could be then used for automation purposes. However, users needed to close the graphical user interface and run such Python scripts using the terminal user interface. Now, in version 4.0, we significantly improved this feature by creating the macro library, a new interface to manage macros in a much more organized way, which also allows users to run these macros within the graphical user interface. Still in the spirit of automation and customization, we introduced a new Python API which enables users to create customized GUI components, and that's one of my favorite new features in this version. As an example, users can create a simple calculator to calculate the necessary boundary layer prism settings based on a desired Y+ value and apply such settings to create the mesh prism layers. To increase the existing value that our customers get from the unlimited scalability of our software licenses, now users can open multiple instances of Helix within the same machine, consuming only one unique license. In Elements, users can prepare, set up, run and post-process their CFD simulations by navigating through the Mesh, Setup, Solver and View tabs. In Elements version 4.0, we introduced the Geometry tab. The new Geometry tab allows users to manage in a much more flexible and organized way the geometry files used in their simulations. Users now can add all necessary geometry files and later decide which ones they want to use for generating the mesh, to set up the case, or for monitoring purposes during post-processing. Now, in terms of mesh generation, this version introduces a very significant and very useful feature called multi-mesh. Multi-mesh is a completely new interface for mesh generation which allows users to generate multiple region meshes independently of each other. In previous Elements versions, users had to create multiple region meshes in multiple steps by importing and merging different meshes. Now, users can mesh multiple regions within the same instance consecutively or simultaneously. Take as an example a heat exchanger. There is a hot and a cold region. To mesh both regions separately, we add a new mesh settings, rename them accordingly, add the geometry files corresponding to the cold region to the cold mesh settings, and do the same for the hot region. Then, we apply the mesh settings for each region, such as refinement surfaces, prism layer settings, and create cell zones for porous media modeling. And when it comes to generate the mesh, we can generate both simultaneously, or one after another. Let's first mesh the cold region. And when the mesh for the cold region is finished, we can mesh the hot region. Other features of the Elements Mesh Generator algorithm include an interface to align the base mesh to a user-defined local coordinate system, an improved treatment for baffles, like the removal of isolated regions when generating meshes for zero-thickness surfaces, and the addition of a 2D feature edge refinement for zero-thickness baffle edges, which helps reducing the aspect ratio of cells around edges where it is difficult to achieve good mesh quality using the standard 3D refinement approach. In terms of case setup, we have implemented a few new boundary conditions. The first one is the non-conformal coupling, NCC, which is a new methodology for coupling patches that presents a few advantages in comparison to the AMI coupling approach. In summary, the NCC approach creates virtual faces between the boundary patches to be coupled, which are the result of the intersection of each boundary patch faces. In this way, the new faces are identical on both sides of the coupling patches, resulting in a perfect one-to-one match when calculating fluxes and other finite volume-related variables. Therefore, full conservation and great accuracy is maintained, while this is a non-issue with the arbitrary mesh interface approach. Even though the NCC approach can be applied for both static and dynamic meshes, including quite complex problems, in this version, the NCC has been implemented for the static boundaries only. We have also expanded the option for users to input flow rate at inlets in other units, rather than just cubic meters per second, since it's quite useful to use different units for several applications. Finally, for joule heating multi-domain thermal simulations, users can now employ a time-varying function for defining electric current applied to solids, as shown in the animation. Another feature that we introduced is the ability to map transient field data on cut planes to boundary conditions of more simplified models. To reduce simulation costs, it is possible now to map the solution from the full model to a boundary condition of the reduced model. In Elements version 4, we introduced the Unified Solver framework, which was a significant refactoring of the code, providing a much more flexible and modular structure in terms of multi-physics problems. In version 4.0, we introduced the capability of solving multi-phase flows inside a multi-region case, such as a CHT analysis. For example, in this animation, we see a hot solid sphere being cooled down by the cold flow of a water stream into an air domain. In Elements version 4, we also introduced a new interface to add completely independent reference frames, which could be used for setting up CFD simulations with quite complex motion. We now introduced the ability to use such reference frames in some monitoring functions such as forces, lift drag, and probes. As an example, the force on the rear surface of an Ahmed body with rotating oscillating motion can now be monitored on the global Earth fixed reference frame or with respect to a moving reference frame relative to the moving body. Still regarding monitoring functions, we added support to calculate statistics of a given field between a pair of existing functions. With this new feature, users can now monitor, for example, the pressure drop between two probe locations by selecting the difference operator. In terms of visualization of the results, we have implemented the LIC surface representation for vector fields. This feature significantly enhances the visualization of flow patterns, making complex flow behaviors easier to understand at a glance. To further support our users, we have ensured that scenes can now be exported in PVD format, allowing seamless visualization in the widely used open-source tool ParaView. With respect to Elements Adjoint, one of Elements' additional modules for topology and shape optimization, we introduced an objective function called threshold pressure, useful for cavitation risk analysis. In Elements Coupled, another additional module for Elements, you could already use a standard pseudo-time step approach for speed-up convergence. In this version, we introduced an adaptive relaxation option that speeds up convergence even more when compared to the standard approach. In summary, this version 4.0 of Elements focused a lot on improving performance and usability to enhance users' experience with our graphical user interface. All our customers can already download Elements version 4.0 in our customer portal. And if you're not a customer but want to learn more about ENGYS and Elements, feel free to contact us at our website, or you can always reach out to anyone from ENGYS team through LinkedIn. We will be more than happy to talk about CFD with you. Thank you, and I see you in the next Elements release.